Hi everyone, I'm Suramya Sarkar and welcome to the Graduate Student Community Spring 2026 Seminar Series featuring Parinaz, and today is April 8 to 2026. We have our graduate student community leadership team, which have our co-chairs, Rodney and Samuel, our publicity team, Avinash, Hafiz, Swapnil, co-treasurers, Siavash and Anshu, our support team, Zareen, Roshan, Rachel, Vibha, Nurayan, and me, and our faculty advisor, Farooq, Professor Farooq Mistry. Our GSC regular meetings are held at Wednesday at 6 p.m. Meetings will be held on Zoom. Please contact Samuel and Rodney for questions and the meeting link, and time is set as per schedule of attending students. You can become a GSC member on Engage. You can scan the QR code you see on the right, log in with your OUID, click on join, and congrats, you're now the member of GSC. You can become a GSC member on LinkedIn. I think it's really beneficial because we do upload our webinars beforehand with the link. So scan the QR code on the right, and that's our LinkedIn page. Click on join, and you will be the member of GSC LinkedIn page. We also have Facebook and Instagram handles, which is basically these two QR codes. And we also update about our webinars there. The GSC YouTube channel, where we upload the webinars which are already done and the recordings. So you can go there and check our previous webinars. The GSC team meeting is held via Zoom, but there is also a bird team room available for all the GSC members to use. We have amenities like couch, whiteboard, coffee pot, microwave, and email if you want access of it. A quick reminder, while attending this wonderful webinar, you will see that there will be a link in your chat box. It will be a link of a Google form. Make sure you fill it out. This helps us to keep track of people attending it so that we can arrange more webinars in future. This semester, GSC focuses on generative AI, and the GSC seminar series bring together leading voices from academia and industry. The main questions are basically how people can work with generative AI to create intellectual, economic, and social value and connect these domains, research issues, methods, and applications, and ways in which generative AI can be designed to link academic inquiry, economic innovation, and social benefit in ethical and equitable ways. We have our forthcoming webinars. On April 22nd, we have Shishir Shah, who is a Chief AI Officer of Kellogg Chair, Professor and Director, School of Computer Science, Oklahoma University. And he is talking about Beyond Real Data, Gen AI, in Cloth-Changing Re-ID. And on April 29, 2026, we have Andrew Ejenakevvi, who is a postdoctoral researcher, School of Aerospace and Mechanical Engineering, OU, AI for Fall Detection and Diagnosis. Today, I welcome Parinaz. She will be talking about a machine learning framework for early lung cancer screening. Parinaz is a high school junior with a strong commitment to STEM and programming and technology. Parinaz has presented at the United Nations Commission on the Status of Women conference at New York headquarters for the past 3 years. She has served as a local ambassador for the Global Techathon Challenge and organized an AI hackathon that encouraged student innovation through her initiative. Tech Together. She partners with groups like Teens in AI, Discovering AI, and the Girl Scouts to deliver accessible computer science education to over 200 students worldwide. Parina has also developed assistive devices supporting people with aphasia and visual impairments. She currently conducts research using AI and data science to analyze CT scans for early stage lung cancer detection. So I pass on the mic to Parina. The stage is all yours. All the best.
Thank you, Soumya, for your introduction. Let me start sharing my screen. Okay, hi everyone. Nice to meet you all. My name is Parinaz Dastur. I'm a high school junior at Stratford Preparatory High School in San Jose, California. Before I get started, I would like to thank my mentors, Dr. Andaz, Ms. Carmarker, and Dr. Pastakia for giving me advice and constantly guiding me through this project. Thank you, Professor Farooq Mistry, for inviting me to present my research at the Graduate Student Community webinar series. And I would also like to thank my parents for their unwavering support in any project I undertake. So to me, research means discovery, living by the scientific method, and constantly learning, using AI to push further. Research means discovery, and it's not only redesigning our solutions, but also how we ask the questions. Because of my interest in both AI and biology, I focused my project on developing a 3D deep learning model for early-stage lung cancer screening. To start, it's important to understand what's at stake. Lung cancer is currently the leading cause of cancer-related deaths in the US, with approximately 130,000 deaths each year. While early detection leads to a 64% survival rate, late-stage detection drops that number to just 9%. Yet fewer than one-third of cases are identified at the early stage. There are several reasons why early detection is so difficult. First, the data itself is highly complex and highly dimensional, meaning that each patient contains hundreds of slices of their lung, representing massive amounts of 3D information that are both computationally expensive and challenging for radiologists to analyze. Second, there is a severe class imbalance. Within each scan, the vast majority of the voxels, or the small cubes that make the scan, represent healthy lung tissue, while tumors only occupy a tiny fraction of the space, which means that the machine learning models are exposed to far more normal than abnormal data. And finally, there is a challenge of morphological similarity. Early stage nodules often look very identical to blood vessels and surrounding lung structures, making them very difficult to distinguish. So looking at the current workflow, radiologists must review over hundreds of CT scans per patient. According to the National Cancer Institute, screening programs produce more negative scans than positive ones, and most detected nodules are benign. Over time, radiologist fatigue becomes a major issue, reducing the ability to detect smaller nodules and increasing the risk of misdiagnosis. Early computer-aided detection systems had high sensitivity but low specificity, meaning that they flagged many false positives. Radiologists then had to review all the flagged areas, which made the process even more time-consuming. To make matters more difficult, the nodules have very similar intensity to blood vessels and soft tissue in a CT scan, which makes it more complex for accurate screening. So for this project, I trained my model on the LIDC IDRI dataset, or the Lung Image Database Consortium dataset from the Cancer Image Archive. Each patient case includes thousands of DICOM files, with each file representing a slice of the lung. There is also an XML file at the end containing detailed metadata, such as the time the patient was screened, the radiologist's annotations of the lung, and image spacing details, and links to specific slices. To add on, each nodule is assigned a malignancy score from 1 to 5, where 1 is benign and 5 is highly malignant. So for my model, I used a convolutional neural network, or CNN. For some background information, CNNs are deep learning architectures specifically designed to learn spatial patterns such as edges, shapes, and textures directly from the data using filters. Early approaches to image recognition required manually defining features and often treated each pixel as an independent variable, ignoring relationships between neighboring pixels, which means that an older model might try to recognize a handwritten 9 by simply comparing pixel by pixel overlap, and then each pixel would determine whether it predicts a 9 or not. But in contrast, a CNN would automatically learn relevant features while preserving the spatial relationships between the pixels. And this allows the model to better understand the structure within an image and make it significantly more accurate and efficient for complex image recognition tasks, such as medical imaging. So several types of CNN architectures exist, but I included some famous ones such as the AlexNet, which enabled early breakthroughs in image classification, and the residual networks that use skipped connections to train very deep models effectively. But for this project, I used a UNet architecture. Because nodules are 3D objects, analyzing a single 2D slice is not sufficient information to predict whether a nodule is cancerous or not. So a UNet is the industry standard for medical segmentation because it captures both what the object is and also where it is located. So it can precisely outline nodules down to the voxel level, and the encoder compresses the scan into key features, and the decoder will reconstruct the scan back out while making its predictions. And the UNet also uses skip connections to preserve more finer details that might otherwise be lost during compression. So I'll go into more detail on how this works. So first we take a large 3D CT scan and break it into smaller manageable 3D cubes, which are 32 by 32 by 32, and they're all called voxels. Because different hospital scanners have different brightness levels, we adjust all the images to a standard brightness so that the AI isn't distracted by lighting differences. So the AI will recognize the density of the tissue rather than being confused by the different machine settings. We create a map based on the expert doctor annotations, which tells the model exactly where the actual lung modules are located. And then a 3D map would tell the AI exactly which voxels are cancer and which are healthy. And then we convert all that data to a smaller scale between 0 to 1. Because AI models perform much better when they deal with smaller, consistent numbers, and it gets very messy with large numbers. Once the data is prepared, it enters the network. So the encoder is basically a stack of layers. Each layer contains filters or mathematical windows that slide across the 3D cube and look for specific features. In earlier layers, they look for simple things like edges and boundaries, and then in deeper layers, they detect more complex features with a combination of the earlier layers. So they would detect something like a rounded shape or an irregular object. And based on the success rate of the last layer, it pools all the strong signals and disregards the less important neurons. And at this point, the model has a compact set of detected features. Next, the bottleneck. So the image is compressed so much that it no longer looks like a lung. What remains is only a mathematical representation of the most important features, or groups of neurons that together classify something as a nodule. And if the right features aren't captured here, the decoder can't recover them. So next, the decoder uses expansionary convolutions to expand the compressed representation back to a full 3D grid, and it would be the same size as the original input. And it builds out a 3D map. For each voxel that it adds, it uses predictions to check whether it's cancerous or not. And then I also have a dotted line between the encoder and decoder that shows the skip connections. Because the encoder loses the exact locations during compression, we use skip connections to pass the complex locations directly to the corresponding decoder layer without breaking it down and then building it back up. So the decoder combines its high-level understanding from the bottleneck with the exact spatial detail from the skip connections, and it allows the model to mark the nodule boundaries very precisely. Next, the sigmoid output. The final layer is a sigmoid function that is applied to every voxel, and it converts the module's raw output into a probability between 0 and 1. So a score of 0.95, for instance, means that a model has a 95% confidence that the voxel is a cancer. And then the full output of the 3D probability map has a score for each voxel across the entire image. So the project involves several redesigns. Initially, in the first version of my project, I used an incorrectly labeled dataset. However, after speaking with a radiologist, Dr. Pastakia, I realized that it didn't reflect the real clinical conditions, so I adjusted the dataset accordingly. And most academic projects rely on clean data, but I intentionally worked with messy, multi-institutional hospital data because I think that's what the model will actually face in a clinical setting. This also made the data loading much more challenging and caused a lot of redesigns, but also far more realistic. I also faced significant class imbalance in the beginning. The early models that I made predicted everything as healthy tissue because there's more probability of finding healthy tissue in a lung scan than tumor. And to address this, I modified the loss function by introducing a weighted binary cross entropy. And this would reward the model with a higher incentive to correctly predict a nodule then correctly predicting empty space. In total, I didn't use a pre-trained model. Instead, I tried redesigning both the architecture and the loss function after seeing that the convention approaches failed on this task. Additionally, I implemented attention gates or standard skip connections that pass relevant and irrelevant information. So the attention gates help the model focus on the most meaningful features to pass in. And each failure taught me exactly what to fix next and push my project along. Next, here are some external configuration settings established before training to control the learning process. So I highlighted certain outliers in the configuration that might be considered abnormal because these outliers make my model unique from the pre-trained medical models currently in the real world. So my learning rate was 1 times 10 to the -4, and I used reduced LR on plateau, which automatically changes the learning rate. So let's say the model predicts very close to the lung nodule, it would yield a very high accuracy. Because of the very high accuracy, it would have a smaller step size and it would get a more precise adjustments to correctly predict the right nodule. But let's say, on the other hand, the model predicts something very far off, then it would increase the learning rate, increasing the step size until it has a more higher probability of finding the nodule. Then once there is overlap, the accuracy would increase and the learning rate would decrease so that it can get more precise adjustments. I had a weight decay of 1 times 10 to the -5, which adds a small penalty to the loss function that shrinks large weights to prevent the model from overfitting. And then the gradient accumulation allowed the model to simulate a large batch size by summing up the calculated gradients over 4 sequential forward-backward passes. So because the data is so vast for this model, simply increasing the batch size only works against us, and the numbers in the calculations increase rapidly, causing an out-of-memory error. So most non-medical AI models use batches that are very large, like 32, 64, or even 128. So it might seem like a low number, but in 3D medical imaging, a batch of 8 is actually considered quite good. The 3D cubes are so heavy that most computers can only handle 1 or 2 at a time. So using gradient accumulation to reach 8, the training was stabilized despite the massive data size. Okay, these ones are mostly normal for an AI model. It increases the number of feature maps from 32 to 256 to allow the network to identify a wider variety of distinct geometric patterns within the 3D volume. And then I have rectified linear unit as the activation function, and it sets negative input values to 0 to introduce nonlinearity and prevent the vanishing gradient problem. A note on this, the vanishing gradient problem is being exacerbated by the very small learning rate because it makes the weight updates negligible, but the ReLU function would help with that. And then the sigmoid function squashes the final output values into a range between 0 and 1 to represent the statistical probability of a voxel belonging to a tumor. And then there are skip connections that recover the fine details lost when the model downsamples. So on the CT scale, -1000 is the density of pure air, and 400 is the density of hard bone. So by clipping the data to this range, we can tell the neurons to ignore everything that is too thin, which would be air, and too thick, which would be bone. And this forces the model to focus on uh, the middle densities, where the soft lung tissue or tumors actually are. So I set a 50% chance of flip or rotation. If I changed every single image, the model might get too confused, and if I changed none, it would just memorize the training photos. So a 50% augmentation of the images is a pretty safe choice. And then a gamma of 2.0 requires the mathematical weight of easy samples, so the model concentrates its gradient updates on the hard samples, like small tumors. And increasing the weight of a cancerous nodule by 10 times is an unusually high number, hence the asterisk. So I covered before in the redesigns that the model was giving 100% healthy output at one point, so this effectively counteracted that to prevent false negatives or the model missing a tumor. Oh, okay. So, based on these assumptions, I got these results. I treated radiologist annotations in the LIDC IDRI dataset as the ground truth and trained my model based on that. I normalized CT scans between -1,000 and 400, and I assumed that everything outside of that would be irrelevant, so that would capture the relevant tissue to predict a nodule. And I assumed that the standard skip connections of a unit pass too much irrelevant data from the encoder to the decoder without making predictions based on that. So I used attention gates to focus more attention on the more precise areas. So the graphs shown here reflect the model's performance along with the visualization. So the FROC curve stands for free response receiver operating characteristic and evaluates ML and medical imaging, and it measures both the accuracy of identifying abnormalities and their specific locations. So the x-axis shows the average number of false positives per image, and the y-axis shows the sensitivity. So on this graph, you can see there's a strong performance at the low false positives. So at 0.05 to 0.2, false positives per scan, the sensitivity is very high, which means that the model detects almost all nodules while producing very false alarms. But the performance degrades at higher thresholds. So at 0.8 false positives per scan, the sensitivity drops to 0.82, and at one false positive per scan, the sensitivity drops to 0.15. So it shows that the model is finding nodules reliably, and the dice of 0.76 shows that the model localizes nodules reasonably well, but the boundaries aren't perfect. So most likely, the model is capturing nodule locations very well, but it might over segment or under segment edges, so it might struggle with irregular objects or fuzzy boundaries. So in closing, my 3D CNN can generalize across multi-institutional CT data from Lung Cancer Image Archive. And because I interviewed with radiologists and surgeons in the field, I was able to tweak my model to fit their needs. And I was able to interview them and see where they needed the most help and where there were gaps in the current solution, and then make something based off of that. One of my key breakthroughs was overcoming the all healthy prediction problem caused by class imbalance in the early training stages. And in the future, I would scale my data to the full cancer image archive repository and add hard negative mining, which was common in the research papers I read, of predictive medical imaging models, which forces the model to learn the harder features to predict the nodule from. And my full documentation and version history is available at my GitHub. So to wrap up, I'd like to pass on the discussion to you guys. I'd love to hear your thoughts on uh, do you see a tool like this fitting into the research or clinical workflow? Where do you see the biggest gap between what AI can do and what it's actually doing? And if you were building the next version of this, what would you prioritize? And then, more personally, what advice would you give to someone who's interested in AI biology research? Also, please feel free to contact me on my LinkedIn or reach out in my email. I'm also happy to share my resume if there are any opportunities available. And any feedback you could give me on how to improve my accuracy is greatly appreciated. Thank you.
Well, thank you, Parinaz. It was really good. I enjoyed the whole talk. I will open the floor for questions, and I would invite certain people. First, Karishma, do you have any question for Parinaz? And
Thank you very much for the talk and for arranging Parinaz's talk, Sarmaya. Two questions. I'm looking at this whole model as a sequence of computations rather than AI. So it's a technical difference, but when I consider it as AI, it becomes a black box. If I consider it as a sequence of computations, it means more to me. Hope that's all right, Parinaz.
Yeah.
What is the I didn't hear you mention this, but what is your take on false negatives, which are equally, in some situations, important to false positives? That's the first question.
Okay. So false positives is missing a tumor when it really is there, and then false negatives would be saying that something is a tumor and then giving someone a treatment when there isn't. So when I talked to radiologists about this, they said that it was equally um, painful to like give someone a treatment when there isn't a cancer because chemotherapy would just degrade you entirely, and then uh, also uh, saying that something is not there when there is cancer there is also um, very dangerous because the cancer would just grow uh, and then it would turn to a late stage. So I think in this case they're both equally uh, as bad, but I actually put more importance on false positives because my model was supposed to flag and pre-filter out for radiologists so that they get less tedious work. So if it flags the false positives and anything that it thinks is a missing tumor, it gets the extra like expert feedback from an actual radiologist that would look at it with human eyes and see if this is actually something to look at. So it's better to flag more than to flag less.
I'll save the next question for the very end. We'll give others an opportunity to contribute to your very interesting work. Thank you.
Thank you.
I would like to invite Janet. Janet, hi.
I'm sorry. I was at a faculty meeting which ran very long, and so I didn't hear much of the talk, so I can't really ask a question, but I apologize.
That's fine. I'll invite other people. I'll invite Percy Baramshah for adding something to her and to contribute something to her research or some ideas. Hmm. Okay. Professor Sefri, would you like to add something to Parinaz's talk or ask her questions?
Well, I was just typing a message thanking her for very informative talk and sharing her research. I don't know much about biology, but I found it very interesting and new approach, and I see her as a upcoming star in our Zoroastrian community, and I look forward to hearing more talks from her.
Thank
No
you.
question.
Please feel free to reach out at my contact or LinkedIn as well.
Yes, Edul Davar. Yes. Would you like to introduce yourself first?
Yeah. Thank you, Parinaz. I'm sure it's very involved, and a lot of it went tangentially off my thinking. But from a practical point of view, we had put you in touch with Shahryar and Dr. Shahryar Andaz, and I'm wondering what type of work you're doing with him, and what is the correlation with actual real life correlation with your model,
Oh, so I actually interviewed Dr. Andas and Dr. Pastakia before, and I asked them many questions about false positives to false negatives. What are the gaps in their current workflow? And before I was making a model that would just take a CT scan and then find lung cancer in it. But Dr. Andas said that most of the problem was actually just reviewing over hundreds of CT scans. And that would be like very problematic for a radiologist because there's radiologist fatigue. And then over time, their accuracy goes down because they're looking at so many lung cancers. So he said to make something that pre-filters out things that you know are healthy and flag the things that you know are lung cancer and early nodules. And then also train like on early nodules and smaller nodules so that you get more specificity and flag more of the stuff that radiologists can then look at and see if it really is cancerous or not.
But would there be a way of taking your likelihood of cancer and correlating to actual life, Sharia's experience on the surgical, when he's actually found a problem and has to do some surgery on it.
Yeah, so in the future I would look to like deploy the model and compare it against a radiologist that is also looking at the CT scans. Um, but right now I'm mostly looking at the evaluation of the uh of like the model's accuracy.
Okay.
There's a question in the chat box by Afreed Mistri saying, where is the model now in terms of percentage accuracy? Would you like to answer that, Parinaz?
Yeah, so the model is actually around the low 80s to 75% accurate, but it has a very high sensitivity to nodules, so it will flag any nodule that is there, as seen in the FROC curve. Oh, I stopped sharing. But so there is a high sensitivity, so it can localize specific nodules. It just can't give the correct shape, which is why it has a lower than usual accuracy. It's about 75 to 80%. But it has location-wise, it can classify 98% of the time.
Okay, so that 25%, which is not accurate, have you discovered or narrowed down or categorized what that 25% is and what's going wrong?
Yeah, so as a speaker said before, the model basically like each neuron and what it's trying to predict is a black box in the end because you don't know what it actually finds in there. But we can deduct that the model might be missing like very irregular shaped nodules because of the way it's getting the correct location but not able to overlap perfectly over it. So that shows that it probably struggles with irregular shapes or like blurry images.
Okay, thank you.
Thank you. So after this, I would invite our GSE leadership team, our PhD students, candidates, Rodney, Anshu, and Swapnil, to share their thoughts, takeaways, or any question if they have.
Sure. Hi, thank you for the presentation. It was really well put together and interesting. I'm not super great at biology. I don't think I have any important questions, but I would say we had a speaker, a GSC member, a couple years ago that presented, I think, using similar techniques and addressing a similar problem. It was on diabetic retinopathy. So he would use a CNN and a couple other machine learning techniques, to view images of the vascular system in the eye. So maybe you could get some takeaways from his papers. His name was Luis Vasquez.
Okay, yeah, I'll note that down.
And I can try to find or reach out to him and send it to you also.
Okay, thank you.
Hmm?
Yeah, it was a wonderful talk actually. And I just wanted to know what the size of your like data set, because the data set for CNN it should be like very large. So
Yeah. Yeah, so the in terms of gigabytes, it's 133 gigabytes, and there are about 1,010 subjects. But there are actually, for each subject, there are many more images. So in total, there are 2,044,530 or so images in the full data set.
Okay, so you must be adding like noise in your model too, right?
Yeah, and
Yeah.
I also wanted to add that the actual data is in DICOM format. So in order to actually like access the data, I needed to use a Python library to process the data and then convert it to something that could actually be used.
Yeah, I did a little bit of similar project, but for material science, not for exact biology, but like almost the model was similar, but little bit of differences. So maybe I will suggest that you can also take a look at like PINN, the physics informed based neural
Okay.
network. Like it is more accurate, and maybe your percentage of accuracy might increase for the long detection, as it is like very real life problem. So maybe you can try that model
Yeah.
too. Yeah.
Okay, thank
Thank
you.
you.
I would, Dr. Devika is in India and her hand is up. I'm sorry to keep you waiting. Would you like to go next?
Uh, Thank you, Surmaya. And it's a very good work, Parinaz. I was just wondering, did you try any of the pre-trained models instead of using CNN and then use a transformer and see how does the accuracy change?
So no, actually, I did not use a pre-trained model. I was tweaking original models, but before I used other types of CNNs. So in my initial model, I used a simple CNN, but that was overfitting and just giving 100% accuracy because it was learning the data just automatically. So yeah, but thank you for asking that.
Thank you. I guess because if you use some deeper model, which is pre-trained, probably you might get different accuracies. You could
Yeah,
try that.
in the future, I would like to compare a pre-trained model's accuracy and the my model's accuracy and also a radiologist's accuracy to see where we get with all of those different numerics.
Thank you. It's good bug.
Thank you.
You'd like to note that down, but after that, I would read the two questions by Karishma in the chat. The two questions are: have you looked at vasculature between because it has a correlation with active nodules? That's the
Um,
first one. Yeah.
okay, just to clarify, can you clarify like exactly what you mean by like vasculature between like active nodules? Are there
Okay, it may not be relevant to what you're doing, Parinaz, but when you're looking at false positives, particularly, let's leave the false negatives out for now, because you said that
yeah.
was less important for your work. When one looks at false positives, in addition to looking at the actual nodule, its shape, and the irregularity that you were finding is a problem with the identification, if one looks at the active, so what's the difference between a scan like an MRI versus a PET scan, or a CT scan versus a PET scan? A positron emission tomography scan looks at the active uptake of 18-fluorodeoxyglucose. What is it based upon? It's based upon metabolism of the tumor. So instead of just looking for a nodule, one can then see whether the nodule is particularly active or a benign nodule.
Yeah.
So if one wants to look at a convoluted neural network simulation, again, I'm leaving the word AI out of it because it's an unnecessary word when one looks at computational neuroscience at some level, just makes another big black box. When one looks at activity of the tumor, and one can't look at it directly if there's no PET data, because if there were PET data, you would be using PET data. So that's a completely separate question. Why are you using scans instead of PET data? So if you're using scans and you're finding this difficulty with shapes of tumors, then looking at the blood vessel network nearby can help, because for every nodule, there will be a blood vessel tumor, a blood vasculature supporting it.
Yeah.
And if
Okay.
you look at the network around it, it's an additional way of looking at the shape of the nodule.
Okay, I think I understand your question. So, first, the changes, detecting a CT scan versus other types of scans, and then looking at blood vessels around it to see if the nodule is an active nodule or a benign nodule. Is that correct?
For your purposes, it's not about it being active or not active, because that a PET scan would tell you. It was to help you with your problem of shape and identification, because your percentage of identification, I'm not using the word accuracy, I'm looking at identifying the nodule, depends on the irregularity of the shape, reducing your what you're calling percentage accuracy. Correct? So my
Yeah.
question was, have you thought about keeping your your simulation as is, and using an additional level of investigation, because the data will be available of the vasculature? So there are two ways of looking at it. I improve it by changing the the computational model, or I make it all better by increasing the levels of computation. Every level of computation that's increased increases the inaccuracy.
Okay.
Amplifies the error. Both. Whereas if you add in more data of a different type, it can sometimes help. It doesn't mean you have to. I'm just asking, have you thought about it? If yes, why? If no, why? That's all.
Okay, so I actually have not looked into that, but I find it particularly interesting. I think with more data, and I'd probably have to expand my data source further, that would be a great step to improving the accuracy of the model and also looking at nodules and their irregular nodules and shapes.
Okay, so the second question by Karishma is, what improvements would you suggest to improve on the limitations of the levels involved in the entirety of skip methodology?
Oh, so is this directed to skip connections between the encoder and decoder? So, yes. So the skip connections in the beginning were very, they would take any type of complicated features of the scan and then send it directly to the decoder without breaking it down and rebuilding it back up. So there are limitations with that because you lose specific spaces and locations where you could be finding a nodule or it could be an irregular density. So that's why I use attention gates to nullify certain skip connections to not pass from the encoder to the decoder based on their weights that the model would give it. So if their weights were greater because it would actually predict a nodule based on that, I would not have it go through the skip connection, instead go through the bottleneck and the decoder to expand it back out.
Nicely given answer. My question was more to help you think about explaining the concept of weights, the concept of what's involved in setting the threshold for weights, explaining to the audience the limitations and the reasons for still using skip connections, both in terms of the computational limitations, but also in terms of the biology. Because when engineers look at biology, sometimes they come up with what some of the people here have said today. I'm not a biologist, so I can't comment. It's very hard when you're looking at somebody who can actually contribute from an engineering perspective. It's really important, from my understanding, to help them to see that this is as much of a business model as it is an engineering model, as it is somebody who's really good at AI could still contribute to it. And you are such a good explainer that you could help them contribute by giving them the right kind of data like you just gave me. So well done.
Okay, thank you.
Okay. I'm just making sure everybody has spoken. I would like to invite Katayun Kapadia, B. Wadia, and Ria Manandar to share something. If they have any takeaways, questions, or anything.
I would just like to, this is Kitayun. I would just like to say Parinaz an excellent presentation. I'm neither a scientist or in biology or AI, but a very interesting presentation for all those present. And good luck with your research and in whatever you do further. You have excellent mentors I see on the screen right here who will help you out. And look forward to having you on one of my webinars soon. When we do for global entrepreneurs, you can be one of the presenters. So I look forward to seeing you in the future and wish you all the best.
Okay, thank you.
Farouk, would you like to go next?
I'm very pleased with what you've done, Parinaz, and the way in which you've explained it, and the way in which you've developed your talk over the last few days. The important thing is for you to be able to publish. And my intent is to put you in touch with professors who are interested in what you're doing and will help you learn how to publish. Because if you do not publish, research disappears, means nothing. It's not archived, it hasn't happened. And there's a certain element of rigor that goes into publishing. It's not just anything that you can publish. It's one thing to talk about it. It's another thing to publish. And Karishma, through her questioning and helping you, has definitely shown you about how to come up with that rigor. So I would strongly advise you to reach out to Karishma and continue talking to her. And Shahrukh Khajotia has sent in his apologies for not being here today. And he is interested in working with you during the summer, remotely, with the idea of writing a paper. So that's the story. So that's my two-penny bit. Back to you, Sonia.
Okay.
Thank you.
Oh, sorry, Parinaz. Anybody else would like to have tell their takeaways? If nobody, then I'd go for it. Okay. Thank you, Parinaz, for the talk. My questions were regarding the size of the data set and how you are training them and what optimizers you were using. And it got all of them got answered one by one because everybody was asking some question or the other. So it was really nice. And I would like to advise to you that if you're doing this research, have you thought about what are the okay, so I have this question that when you are talking about it can be any model. It can be any model. I'm not talking about the particular data set. Okay, so I'm not talking about the particular data. Here you're using a medical data. It doesn't have to be a medical data. It can be any sort of data, and you're doing it by CNN. And I want to know what are the ways you are filtering the data and then you're adding noise, correct?
Yeah.
So what are the ways are you filtering the data? And what sorts of noise are you using to increase the space or increase the detection space when it comes to different variety of detection? And can it be used for any other sort of data set? That's my question.
So this model is, oh wait, so just to clarify your question, it's mostly about the noise and how that data set.
So first you're removing certain things from the data. You're filtering it.
Yeah.
And then you're adding noise to it. I want to know how you're doing it.
Okay, so in terms of like cleaning the data, filtering it through, I look at each voxel, and if it is a positive or radiologist annotated, I would add it to nodules, and then that nodule would be normalized, and then it would be fed into the CNN model. And then there are a list of healthy voxels and nodules that are voxels, and then I normalize all of them and put them through the CNN network.
Mm-hmm.
And then I create a nodule mask that will map out the radiologist annotations, and that would give the precise location to look for when rebuilding out the complete prediction of the CT scan.
Okay. So can you say that this is a classic example of human-computer interaction where the radiologist is telling that, okay, this can go in, and where the computer is filtering the things which cannot go in? Can you say that this is an example of a human AI or human-computer interaction?
So where
you're going through the radiologist, where the radiologist is saying, okay, this can go in. Yes. So that's a human aspect. And then you have the computer aspect to it.
So mostly when looking at a deployment of the model, the radiologist aspect would be to give like a patient, which would have the CT scans, and then the computer, which has already trained on the data, will then go through the CT scans, and I would run my model through that and give a prediction of each of the CT scans with where the prediction is localized. So, but when I'm filtering out the data, it's automized. So there are, but the data is annotated by radiologists in the beginning. Does that
Okay.
answer your question?
Yeah, it does. Thank you. Karishma has her hand up.
So here's a fun question. By the way, got a compliment from my mother, Jaru, who's listened to you today. Well done.
Okay.
Here's a question for you. What would you want? So now you've got a lot to add to the medical field. So let's look at it from a different perspective. What would you want from the medical field in terms of advancement in order for your model to benefit so that your model can add to the medical field? Now look at this from a business perspective. Every scan, I'm asking you to do this for a reason. We've got Ketayun here, you've got Adel here, and you've got engineers. Every step in engineering costs money. Every time a patient comes in, it's somebody's money being spent, in addition to time and the pay that you're giving the doctors. So to bridge the gap between business, engineering, and biology or medicine, somebody like you could be extremely valuable. Because your model could then, or you could then say, in order to make a model like this more effective, this is the sort of data I think would be very useful if you could capture during or after the scan, even from the notes or the scan or the number of scans or the time between scans, because every time a scan is taken, that data can be accumulated. It's not done usually. So how are you going to direct the future of medicine in a business, engineering, and medical overlap?
Okay, so that's a very interesting question. And I kind of like thinking about that as well. Like I was thinking about that throughout looking at the project. First, because of the data loading aspect, like it was a lot of work taking the DICOM files and then converting it, and then I had to use NVIA data retriever, which was a specific data retriever that is like very hard to operate, and like I had to like go through these lists of documentation to find out like how to use it. So I would first, in terms of least expensive option first to do would be to get a better data compiler and processor to process the data more effectively for programmers to then use it to make CNNs based on that. And then secondly, then like the timing the patient was screened and then how the lung cancer would have evolved over time as they like continued and from early stage lung cancer then to late detection and what happened for the patient. And I know that that is extremely it cost like there's a lot of cost behind that. So I know that like a radiologist that I have talked with said that that would be extremely beneficial as well, especially looking at how radiologist annotations changed over time And one way I would use that in a CNN would be to look at how the different scan changed and see how my model would start to predict, and how when it would start to predict the cancerous nodule, and when a radiologist would start to predict the cancerous nodule, and like compare those two timings.
Very good. When you think of all these answers and questions, also think that you are actually looking at one more cost. The cost of missing tumors, therefore the cost to life itself. That's one more thing that you're adding to. So my suggestion is look at the significance of the process of your work. Don't just get turned on or off when things go well or badly. But the process that you're involved in is extremely valuable. So thank you.
Okay, thank you.
Okay. I'm now going to stop the recording, and it's